Trillions of dollars in capital now rest on a single assumption, that when a large language model hallucinates, it is because the machine is defective. Compare this to a traditional programming compiler. When it encounters a missing variable or an undefined behavior, it doesn't improvise. It immediately halts and returns an error. A large language model functions differently. When it hits a logic gap, it uses statistical probability to generate a plausible assumption. It fills the silence with a guess. This behavior is a direct reaction to underspecified input. Hallucination is the side effect of providing a model a gap instead of a specific instruction. We are treating the machine for a disease that is actually located in the human input. The industry's current response is prompt engineering, a discipline focused on extracting better results through tone, structure, and few-shot examples. But a prompt is merely a delivery mechanism, a wrapper. The core is the mathematical specification of intent, defining what is actually built. Changing the wrapper shape cannot fix missing logic at the center. The model will still encounter undefined behavior, triggering gap-filling side effects. A complete specification leaves the AI with no room for judgment. Every input, every rule, and every exception is named, turning execution into a mechanical process. Optimizing the wrapper while leaving the core empty ensures that AI output remains inconsistent. Consider a developer using AI to build a private, encrypted peer-to-peer messaging application. In most projects, requirements exist only as informal descriptions. The developer defines the data, the logic, and the UI independently and manually. Building this application requires 4 distinct layers: UI pages, database schemas, business logic services, and the unit tests. In standard practice, these layers share no enforced contracts. The relationships between them are unverified, creating 4 distinct boundaries where the AI must guess. These unverified boundaries ensure structural failure. They create the exact gaps where the AI is forced to improvise before the code is even generated. Integration breaks when a generated UI requests a hook that does not match the signature defined in the service layer. It happens again when a test suite simulates database behavior that is inconsistent with the actual schema. Each failure requires a manual correction cycle. Based on the documentation for this project, that averages 3 to 6 cycles per boundary. This totals 12 to 24 additional correction cycles just to reach a working integrated application. Manual correction cycles consume time and budget, while eroding the specification's role as the single source of truth. The Software Development Prompting Framework, or SDPF, mandates a complete definition of the system before any code is generated. Phase 0 of the framework enforces a target of 0 unverified boundaries. Every hook, type, and method reference must resolve to a named definition in a corresponding layer. This locks the contract. Every UI hook resolves to a specific service, and every service references a defined schema. The red dashed lines of guesswork are replaced by structural columns. When this locked specification reaches the model's ability to improvise is suppressed. There are no undefined instructions left to resolve. By eliminating inconsistency at the source, the AI produces code that integrates on the first submission, satisfying every structural contract before the developer begins manual testing. If the LLM is a precise compiler, then our current methods for ranking AI models are measuring the wrong capability. Standard industry benchmarks measure a model's ability to guess under uncertainty. This graph shows why massive models dominate. They are better at gap filling when the input is incomplete. But when we test for execution fidelity, the ability to follow a locked, complete specification, the ranking changes. When the input is complete, the execution of a 7 billion parameter model matches the precision of models 100 times its size. Smaller models match the fidelity of their larger counterparts once they receive the complete input they were designed for. This challenges the trillion-dollar investment thesis that continuous infrastructure expansion and larger parameter counts are necessary to achieve reliability. This challenges the scaling thesis. If reliability is a function of the specification, then massive parameter counts are merely treating a symptom of poor input. A large model's ability to fill gaps masks the danger of underspecified input. It allows engineers to build enterprise systems on a foundation of guesswork. There is a commercial incentive for tech giants to sell continuous expansion. Human input discipline is actively bad for a business model built on selling more compute. The return on another data center is marginal compared to the impact of teaching engineers to write complete specifications. Software development must be rebuilt from the input side, treating the specification as a permanent governing contract. The developer's role shifts. Time spent writing implementation code drops toward zero, replaced by high-level system specification. The model is ready. It has always been ready. The specification is the program, and the AI is the compiler. Success in this environment moves away from those who hoard the most compute toward those who exercise the highest specification discipline.